Swayam Prabha. Digital India. Educated India.
So, welcome to the NPTEL certification course on architectural acoustics. We are now in the 7th week and this is the last lecture on the 7th week and structure bound sound transmission 2. So, in the last lecture we have discussed about some of the primary parameters of a structure bound sound, how it is influenced by those parameters, and in this lecture we will have two learning objective once again, and we will actually going to relate the mass, stiffness and the damping in the vibration transmission point of view, and also we will going to discuss a bit of the impact insulation. So, before go to this particular the relation between the mass stiffness and the damping, let us discuss some of the barrier of the trenching. So, if you remember in the last lecture we have talked about there are the source, there are the path and there are the receiver. So, sometimes a structural discontinuity in the path gives you the noise reduction, structure bound noise reduction. Sometimes some kind of a mounting in a particular machine will actually stop or reduce the propagation of the sound from the source itself. Sometimes we sometimes have to protect the particular the building or the noise sensitive area by virtue of the sound transmission, which can be done through the trench barrier. In the trench barrier, in the soil itself or in the ground itself, two trench has been made and a vibrating machine has been placed, and because of this trench, and this trench may be filled with some kind of the fine or the medium sand or felt layer with this particular dimensions can actually going to reduce the propagation of the sound. So, here in this particular zone of the soil or the base, there will be a amplitude of the vibration will be very high, but when it is crosses to there is a damping, and due to the damping and the absorption of the sound over here or the vibration or the mechanical energy over here, the amplitude will be reduced down. So, by virtue of this trench barrier you can actually protect this particular vibration sensitive buildings also. We can also think of this kind of a trench barrier through some kind of a wooden barrier or kind of a metallic barrier, where again a railway or a industrial area which is having a vibrating zone as such can be safeguarded. This vibration propagation of the vibration can be safeguarded through this particular trench, and this noise sensitive zone, the vibration sensitive building can be taken safeguarded by this trench also. So, we can use some kind of a wooden barrier or the metallic barrier or some kind of the flexible the padding systems over this particular as a trench. So, next let us go to, if we going to this kind of the vibration isolation, of course, in case of the object and the machines and the systems with having some kind of a spring and the damping, then if you remember in the last lecture what we did is that is a free vibration where there is no damping. A machine is freely vibrated with its own natural frequency. Here also it will be going to be vibrated by its own natural frequency. The only change is that here there is a damping dashpot is been made. That means, this machine is now on kind of a layer, which layer is a damping layer and which can be act as a vibration isolator or going to absorb the mechanical energy. So, what will be the fundamental free body diagram of this particular system? A mass is acted by a force, and this force is external force or the operating force, and due to this force there is a equal and opposite kind of a force will be developed, or the resistive force will be developed, one through the system's stiffness, which is k into x, and 1 through the damper, which is we have been introduced over here, which is a damping coefficient c into x dot. X dot is the dx dt, that is the velocity of the particular movement, and with that force, because of this F and these two forces, the mass will be actually having some kind of a resultant acceleration and x double dot, and m x double dot is your force that is experienced by the mass, and this is the resultant force F minus k x minus c x dot. So, if you rearrange, the equation will be like that, m x double dot plus k x plus c x dot equal to 0. So, this is again a second order the differential equation, and the solution of this differential equation will be like this, exponent or in exponent terms, and there will be two roots r 1 and r 2 can be found out from this equation. So, by virtue of this damping and this by virtue of this criteria of the damping, a critical damping amount of critical damping can be found out with C critical is equal to twice under root k by m. So, what is critical damping is that this much amount of damping if you can provide, that is the fullest amount of damping a particular machine may need, but we can provide over an access to that also. Sometimes we can give some kind of a under damping case also. So, a damping has to be provided by virtue of some kind of the layer or some kind of the damper or some kind of a spring or some kind of a flexible padding. So, this damping factor is defined as xi is equal to C by C critical, where C critical is your twice of under root k m and C is the actual value of your that particular damping value of the layers you are going to provide. So, please remember that this C critical is a factor, or the parameter of the C critical is depend upon the mass of the machine which is going to be vibrated and the system stiffness, whereas this C, which is the component which is actually going to be provided, comes from the particular layers damping character. So, one possibilities are that the C is less than C critical, where xi is less than 1, which is the under damping case. There can be another possibility as the C is exactly equal to the C critical. So, the xi is equal to 1, that is called the critical damping scenario, and there can be another situation where C is more than C critical and the xi is more than 1. So, it is over damping scenario. So, which one is good and which one we will going to adopt, we will let us see. So, suppose there is a mass and this particular the object mass, its stiffness and the damping is there. So, it is a particular vibration scenario. So, there is a force, impressed force because of the operation, which is F naught F O, and because of this force and because of all the mechanism happening over here, it has transmitted some kind of a force also F t. The ratio of this F t by F o, the transmitted force by the impressed force, is called transmissibility ratio. Transmissibility ratio, and this transmissibility ratio formula, if you just see this ratio, this T r has to be minimum. Why T r has to be minimum? Then whatever may be your F naught is, F t will be minimum. And as F t will be minimum, the transmission due to this vibration will be minimum and my noise propagation also will be minimum. So, what are the factor actually that will play a role in this particular T r? Let us see. The first factor is the natural frequency of the machine. Yes, a particular system, a particular vibration system has its the natural frequency by virtue of its mass and stiffness. Next is operating frequency of the machine. Again what is operating frequency? If you stirred the machine, some electricity or some kind of the other energy the machine start vibrating, the pump is start pumping the water, the AHU start sending the air. So, that particular operation time, this operation frequency is actually happen to be there in this particular system. So, operating frequency may not be fixed. Suppose there is a voltage fluctuation, so operating frequency may change due to the voltage fluctuation. There is some kind of a mechanical problem in the gear or maybe some kind of assembly, operating frequency may change due to that. So, there is a kind of a set of operation frequency because of those kind of a thing, but there is a designated frequency, operating frequency is there for a particular machine when it is running in a full and the idle condition. What is the third parameter? The third parameter is the damping factor. So, if you use more amount of damping, critical damping, the overcritical damping or the undercritical damping. So, because of that your propagation of the sound, your transmitted force will going to change. So, these are three important factors that will play a role in the transmission ratio. Now, let us see how this three factor can come through a equation, and I can actually find out the TR, the transmissibility ratio, if I know Fn, Fo and Xi. This is the natural frequency we have already discussed. Now, this is the transmissibility ratio equation. I am not going to derive this equation. Any vibration isolation, vibration mechanical engineering books, you can find out this equation and the derivations on that, but this equation I am going to discuss over here because this is very interesting, and being a architect or at least being a a particular person who is going to deal with this kind of a noise propagation, structure borne noise propagation, I believe we should know the ins and outs of this transmissibility ratio equation. This is a big equation, no doubt, but if you see there is a very good similarity. This I have told you there are three factors only: operating frequency, natural frequency and the Xi. Xi, what is Xi? C by C critical, that ratio. So, actually if you see this is a ratio format, F O and F N, this ratio. So, this is unitless and Xi is also unitless. So, this is particularly unitless kind of a character. Now, if I say that this R is a frequency ratio, that is F naught by F n, I can reduce this big equation to a smaller equation. Just I am replacing what? I am replacing F naught by F n by capital R, nothing else. Now, there are three criteria. One is full edge damping, I am providing Xi equal to 1, and suppose I am providing no damping, this Xi equal to 1 is the critical damping, I have provide fullest amount of damping. The second case I am providing 50% of the damping, so Xi equal to 0.5, and another case I am providing no damping, Xi equal to 0. So, just I place the machine on the particular floor itself without any kind of the added the flexible layers or so. Let us see what, how and this particular Xi values change the TR value. The first case where this particular Xi is equal to 0, or maybe that was the third case in the last slide, no damping, Xi equal to 0. So, if I put 0, so this is 1 and this is also 0. So, and this under root comes out 1 minus R square. TR equation is now very simple, 1 by 1 minus R square, where R is equal to F naught by F n. Now, if the 50% damping is there, this is Xi is 0.5. So, put Xi equal to 0.5. So, 0.5 into 2 equal to 1, 0.5 into 2 equal to 1 also here. So, 1 plus R square under root 1 minus R square whole square plus 2 R square. I think this is a slight typological error, this will be only R square and we will rectify it. So, then next one is if it is a full edge damping. So, the Xi is equal to 1, and now if you put the Xi equal to 1, you will get this 1. So, this is 2, 2 square is 4 R square, this is also 4 R square, and this is remain as 1 minus r square whole square. So, this 3 equation of TR comes predominantly for xi equal to 0, xi equal to 0.5 and xi equal to 1, and let us see how it will change its character when I will have different frequency ratio. So, in that you see in this table what I did is that the R is given in the blue this row. So, R the frequency ratio starts from 0, 0.25 like that, 0.5, 0.75, 1, this is 1.414 is under root 2 and then 3, 5, 10 like that. And we use this equation for xi equal to 0 and xi equal to 1 with this equation, and we plotted the thing. And you see if the xi is 0 case, when there is no damping is provided, and if your the frequency ratio is 1, that is your operating frequency is equal to your the natural frequency, the TR the transmissibility ratio is infinity. That means, you will be going to propagate, the sound will be infinite to be the transmission force will be infinite. So, that is the resonance, that is the creation, the resonance effect, and you are taking no consideration, no damping for that. Similarly, if it is 1, in that case when it is equal, you have provided fullest amount of damping from infinity to it reduced down to 1.21, only 12% increase in the transmission from the operative force also. So, with this two data set of data, you can draw a graph. I have this is the y axis is the transmissibility ratio and x axis is the frequency ratio. So, it is always going to be better if the transmissibility ratio is less than 1, and then only I can say that what may be the operating force, my transmission force is less than that. But this blue line is what? Xi equal to 0, it is infinity when it is 1, when it is 1 it is infinity, and then it is gradually decreased down, but this red line is for the fullest amount of damping, your TR is under very controlled way, I mean it is following a very controlled manner. So, definitely the fullest amount of damping is going to help, it will reduce down your amount of vibration or the force propagation due to the vibration. So, let us do this for the 50% of the damping also. I am sorry, this is again a typological error where this 2 has to be eliminated. In the PowerPoint slide I will change it and I will upload it. This R is here, and for this T values this is the particular damping value, this particular damping value is this, and for that we can also now draw a graph, another graph which is a black color one, which is for TR equal to 0.5. So, even if you give a 50% of the damping, yes, it is bit increased with respect to the fullest damping, but still it is under control, still it is under control. So, we can think of some kind of the damper in a particular machine below the machine to reduce the propagation of the sound. But my dear, this is not so easy. If you see this particular transmissibility ratio curve or the set of curve, I can see there are 3 typical zones. The first zone, I see this particular first zone where this frequency ratio is 0 to 0.5 or so, where if you give damping or if you do not give damping or if you give fullest amount of damping, all are flying from 1 and very gradually it is increasing. So, I have written that if your frequency ratio is in between this, your natural frequency and the operative frequency ratio is in between 0 to 0.5, you can give damper, but that is very uneconomical, because if see here what is the distance or the damping if you do not give and if you give 100%, this is negligible amount of change will occur. If I go back, if you give 0.25, if you do not give anything it is 1.07, If you give fullest amount of damping, it is 1.05. See the change. Giving nothing is 1.07 and giving 100% is 1.05, only 0.02 fraction of change if you give fullest amount of damping. That is why I have written over here this zone 1 0.0 to 0.05 use of damper is uneconomical. You can give, but it is slight change will be occur. The next zone is this zone where 0.5 to 1.41 for root 2. In this zone, if you see, if you do not give, it will fly away. The TR is very high, infinite in fact for 1, and if you give, then this is reducing and reducing by maybe less than 1.5 or so. So, if your frequency ratio is in between 0.5 to 1.5, use of damper is highly necessary. You have to have give the damper, otherwise it will propagate the sound or the vibration like anything. Again, if I go back to the this particular table, this is in this zone. So, if you suppose 0.75, if you give, if you do not give, it is 2.28. If you give full, then it is 1.15, or if it is, if you give 50% is 1. So, you have to give the damping over there. If it is 1, it is obvious infinite and it is reduced down to like that. But in case of root 2, all are equal. Now, this is the second zone. So, you have to have give the damper for those zone if your frequency ratio comes in between 0.5 to 1.5. Now, there is a third zone also. The third zone is when your frequency ratio is greater than 1.414 or root 2. See what happened. If you do not give, follow this blue line, do not give, after the root 2 line, this is here. If you give full amount of damping, you are above. So, what does it mean? If you give the full amount of damping and your frequency ratio is the higher than 1.41 for root 2, you are enlarging your TR value. You are enlarging your TR value by putting this damper. So, use of damper is prohibited. You should not use the damper if the frequency ratio is more than root 2. If you see the table once again, suppose it is your frequency ratio is more than root 2, that is your suppose 0.5, 5. If you do not give any kind of damper, it is 0.042. If you give full amount of damping, your TR value is 0.39. So, why should I give damping? Why should I give even 50% of the damping also? Because it is give me 0.21, it is 0.042. So, below this, below root 2, those area, or maybe in another way, if the ratio is more than root 2, better to not to provide the damping. So, that is why I have written this is the red zone, the third zone, when the R is more than root 2, use of damper is prohibited, do not use the damper. So, by virtue of this particular equation, I have told you this equation is very tough to derive, very much I mean the mathematically very tough to derive, but it has a very interesting role to play in the vibration transmission. It suggested that just closing my eye and putting some kind of a damper in a particular machine is not going to actually going to happen, not going to help me. I have to first find out what is the operating frequency, what is the natural frequency. I should know what is the ratio between them. If the ratio is in the first zone, it is uneconomical. If it is the second zone, I have to provide the damper, and if it is in the third zone, we should not use the damper, because if I use the damper, the TR will be much more the higher, and it will actually propagate much high amount of vibration. So, next let us go to the impact noise. The impact noise are noise that made by some kind of a sound in a particular horizontal floor by some kind of a impact, maybe the footstep, maybe some kind of a machine tapping on the particular floor, or maybe sometimes it may be a dance floor or some kind of a aerobic activities also. So, for that also sometimes it's happened. So, the noise will propagate from the upper floor to the lower floor because of this impact. So, there are various way to control the first one is the cushion is the best one, is the cushion for this particular impact control. We can create some kind of a float of the floor, the floating floor, where you can use the some kind of a arrangement where the particular floor is floated over the structural floor. We can also use kind of a suspended ceiling system and use some kind of a absorber and the cavity kind of a attachment below the structural floor to avoid the propagation of the noise from the floor above to the below. And also we can use some kind of isolate all kind of a piping and all those kind of a the work which is actually propagating some kind of a fluid, and then because of that some kind of a vibration, and we can isolate that one to reduce down the impact borne sound also. So, very similar to the STC, that is the sound transmission class, there is also impact insulation class or IIC rating system is also available for the any kind of those kind of a floors, where again the 1/3 octave band from 1000 to 3150, those 16 1/3 octave band is actually taken, and a particular single number is try to find out a indicatory number which will be give you some kind of a sense of reduction of the dB from the source to the receiver the area. So, again it has to be done like this, it is the 16 frequencies and you test each frequency and see the what is the reduction in the dB, and this will be plotted haphazardly, and the way we did in case of the STC, the same procedure we can follow. If you remember, we take the first 6 frequency, take the average, draw a straight line, then decrease by the 5 dB within this 5 dB zone, and then again decrease by 15 dB within that 15 dB zone, we get the contour this contour. In that case it was called the STC contour, in this case it is called the IIC contour. And if you see, remember, this is the other way around, the STC contour was something like this is going like this is other way around, and similar to the STC contour, the corresponding to the 500 frequency sound, the when it is striking this contour and you go vertical horizontal, and this particular value in the transmission loss case will be the your the IIC value of this particular material or particular floor. So, there are typical, I have listed down some typical floor or typical material which actually used for any kind of a floor, and the corresponding IIC value. Ceramic tiles is less, the vinyl flooring is also very less, but if you go for the carpet or any kind of the floating floor with the concrete and the mineral fibers and all, it will be very high. So, I have sketched also some of the cases if you want to have a kind of a floating floor. So, this is your the structural slab, this is your structural slab first layer or the bottommost layer. We can prove some kind of a blanket, this is the second one is the blanket, the resilient blanket, which is something like this, a blanket you put, and then you put some kind of this black color thick line is the waterproofing membrane, and over that you put 75 mm screed concrete, and the over and above this is your desired floor finish is a compacted kind of a the floating floor construction, where each and every layer the structural the layer structural slab and the top floor finish and the screed concrete layer is sandwiched with the waterproofing membrane and the resilient blanket. We can also float the floor a little high. You see what we did is that there is a structural slab which is this, and over that there is a some kind of a resilient blanket layer. It is maybe through layer or maybe just below this 50 by 50 wooden plank. So, this is that resilient layer. Over that this wooden plank runners are run, this is the runner, and over that, which is not shown in this particular photograph, we may place a 12 ply, and over the 12 ply again you put that waterproofing membrane, and after this waterproofing membrane you put your screed concrete and the desirable floor finish. So, here what happened is that the structural slab is isolated from the above floor by virtue of this wooden membrane and some air gap in between, and also it having some kind of a soft resilient blanket layer, which will definitely going to absorb the footstep noise or the impact borne noise or so. So, that is going to be the end of the week's lecture, this 7th week lecture, and this 5th lecture of the 7th week. As usual, I have some homework for you. The first one is the theoretical. You have to state the methodology and step involves to impact insulation rating of the floor. Please remember, this is very similar to the STC. I have described the STC in the fullest way in the lecture number I think 33, and the impact insulation rating is almost similar to that. So, you have to find the steps and methodology by yourself. And another one is bit mathematical. Suppose a machine is having its stiffness of 10 to the power 5 Newton meter and mass is 10 kg, and the operating frequency is suppose 75 hertz. So, this stiffness and mass will give you the natural frequency, and operating frequency is 75 hertz. Now, my question is, do you recommend any kind of damping solution, damper, to control this mechanical vibration? Do you? And if you say yes, why? If you say no, why? So, you have to give your justification of your statement. So, these are two homework for you, and in the next lecture next week we will go to the environmental noise control, and that will be the last week of our this program. So, I have taken help of these 4 books for this particular lecture number 35 on structure bound sound transmission 2. Thank you for hearing me.